Hello and welcome to a quick video on approximating square roots in your head. First of all, let's take a number like 39 and think about a clever way to rewrite it. We actually write it as the nearest square number, which would be 36, plus the difference, which would be 3. And then we can factor out 36 from the square root, giving us 6 outside, and then 1 plus 3 over 36 inside. Then we can rewrite the square root as simply this bracket here, raised to the power of 1/2. Next, we can apply the Taylor approximation to a general expression of this kind here, 1 plus r raised to the power of a, and then realize that if r is very small, we can approximate this as simply 1 plus a times r. Applying that to the statement above, we can see that the square root of 39 is approximately equal to 6 times 1 plus 1/2, which has jumped down, multiplied by 3 over 36, which in the end gives us 6.25. We can also check the result by computing the true value of the square root to be 6.24499 something, which is quite close to the 6.25 that we got from the approximation. So in general, we can write that the square root of x is equal to 1/2 multiplied by the nearest root added to the original number over the nearest root, like so. So now let's actually check in Python how accurate this approximation is. Does it become more accurate or less accurate if we plug in a higher number? What's actually going to happen? So first, we're going to import some libraries, numpy and matplotlib, and then we're going to use this little trick here for finding the nearest square. It's actually a trick I found online somewhere else, so you can check that link out if you want. And then we can implement the function from above to get the approximate square root, like so. Then let's actually try and plot the approximation as well as the true square root to see what's going on here. So we can see that the square root of x is the orange line here, and the approximation is the blue line, and they seem to follow each other quite closely, at least for the first 10 numbers or so. Let's see what happens if we increase the number of entries. Yeah, we can see it still stays pretty close to the orange line. So now let's investigate what the error is, like both what the difference between the square root and approximation, as well as the relative error. So we can plot both the absolute error and the relative error, like so. And we can see that the sort of absolute difference between our approximation and the true value seems to decrease, like basically 1/8 divided by square root of x. And that's just something I found by just playing around with these values here. I couldn't actually really derive why it has to be 1/8 divided by the square root of x. So maybe you can take a look at the formulas and figure that out for yourself. But if you look at the relative error, we can see that already here at 10, we have a relative error of about 10 to the negative 2. So that's a 1% error already at 10 here. And it keeps getting better and better and better the bigger number we plug in. So it's actually quite a useful approximation with a fairly small error if you plug in a larger number. So anyway, I hope you found that interesting. Feel free to check out the source code in the description, and I'll see you in the next video. Bye bye.